Section 2.6, Families of Functions. The objective is to analyze transformations of functions. A parent function is the simplest form in a set of functions that form a family. A transformation is each function in the family is a transformation of the parent function. So they take the parent function, they move it, for instance, right or left or up or down or stretch it or shrink it, those kinds of things. A translation shifts the graph of the parent function horizontally, vertical, or both without changing the shape or orientation. For a positive constant k and a parent function f of x plus or minus k is a vertical translation. So there was supposed to be a comma here. That's why it read kind of funny. So for a positive constant k and a parent function f of x plus or minus k is a vertical translation. So plus k would be up k units. Minus k would be down k units. For a positive constant h, f of x plus h or f of x minus h is a horizontal translation. So for this one, it's actually a little bit different. If you're kind of looking at this, it is on page 99. So on this one, the x plus h does something and the x minus h does something else. And it's kind of opposite of what you might think. X plus h would be left h units. X minus h in the parentheses would be right h units. Now, the reason it's like that is because you're kind of looking at it like an equation. X plus h equals 0 would give you x equals negative h, which would mean left h. If you look at x minus h equals 0 and you solve it, you get x equals h, which would be right units, h units. So we talked about the plus k, the minus k already. We talked about the plus h shifts it left, the minus h shifts it right. So let's look at one. So how are the functions y equals x and y equals x minus 2 related? So the y equals x is the parent function. So what you do is you look at that one and you graph it. And I'm going to do these in a couple of different colors so you can kind of see what happens. So if you are looking at y equals x and you looked at a table of values, wherever those points are the same, that's where the points would be. So 0, 0, 1, 1, 2, 2. Or you can look at it like this, y equals x plus 0. You would have it crosses at 0 and moves up one, right one, or down one, left one, both ways. So I'm going to put quite a few dots in here because I'm not going to use a ruler. So this is the parent function. Looks like that. Now, if you think about the next one, y equals x minus 2 would move every one of those ordered pairs down 2. And if you look at it also, the 2 is not in the parenthesis with anything. So plus 2 would be up 2. This minus 2 would be down 2. So this minus 2 means all the ordered pairs that you have, move them down 2. So it becomes 2 down for each one. And then we draw that one in. Okay, so this one is y equals x minus 2. And the other one was y equals x. Okay, so when you're looking at this in terms of ordered pairs, 0, 0, and 0, negative 2. So the y value is the one that changed and changed from what it was to 2 units down. If you're looking at this one was on page 100. They used a table of values. I don't really like using a table when the function is so easy. We can certainly do that for the next one. So be able to recognize, what does a line look like? What does a parabola look like? What does something like that look like? So for this one, if you didn't know that the x squared part of it stood for a parabola, that would be something that you would want to use a table of values to find out. And it says we want to translate this one up 5 units. Excuse me. And it does say make a table this time. So when you're looking at this one, what would y equals x squared look like? What would y equals x squared minus 1 look like? And then you're going to move it up 5. So we need to move the initial y equals x squared graph. We have to do the minus 1, which means you're moving it down 1. And they also say they want it up 5. So it says make a table. Okay, so I'm going to do it a little bit different than the book does. I'm going to do 3 columns. So we're going to have x. We're going to have x squared. And we're going to have x squared minus 1. And then we will do x squared plus 4. Okay, so let's do some positive numbers, some negative numbers. Let's do negative 2, negative 1, 0, 1, and 2. So if we take and square x, we get negative 2 times negative 2, and you get 4. Negative 1 times negative 1, you get 1. 0 times 0 is 0. 1 squared is 1. 2 squared is 4. And then if we take those values and we subtract 1 from them, we're going to take our x squared column and just subtract 1. So 4 minus 1 would be 3. 1 minus 1 would be 0. 0 minus 1 would be negative 1. 1 minus 1 would be 0 again. And 4 minus 1 would give you 3. And then when we take those values and we add 4 to them, we have to go back to our x squared column and add 4. So I'm looking at this column right here. So now that we have x squared plus 4, we go to our x squared column and we add 4 to it. So 4 plus 4 would give you 8. 1 plus 4 gives you 5. 0 plus 4 gives you 4. 1 plus 4 gives you 5. And 4 plus 4 gives you 8 again. So now we plot all of these ordered pairs and then go from there. Okay, so let's graph the ordered pairs. I'm going to do them in color. So my first ordered pairs are going to be negative 2, 4, negative 1, 1. So I'm using the x in the x squared column. So negative 2, 4. Negative 1, 1. 0, 0. 1, 1. 2, 4. Okay, and that's this one. Okay, my next one I'll do in green. So I go back to the negative 2, 3. So negative 2, 1, 2, 3. Negative 1, 0. 0, negative 1. 1, 0, and 2, 3. So notice how each one of these went down 1, and the equation says x squared, what we had before, and the minus 1 means down 1. So if you graph the parent function and go, oh, that means down 1, all you have to do is take that parent function and go down. So that's what this one looks like. And the last one we will do in orange. Or no, let's do something blue. Let's go blue. So if we look at the parent function and we look at the plus 4, that makes this one up 4 from the parent function, not from the previous one. So we're looking at negative 2, 8. Negative 1, 5. 0, 4. 1, 5. And 2, 8. Okay, so notice again that if you look at your parent function, which is the pink one, and you count up 4, that gives you that point. Up 4 gives you that point. Up 4 gives you that point, and so on. So looking at the parent function and knowing what it does, that helps a lot. Now, how did they go? Did we use the up 5? We absolutely did, because if you look at this, y equals x squared minus 1, and if it's up 5, we're just going to add 5 to it. That's where that equation came from. Okay, so I didn't change anything, I just didn't say that, and I should have. So that's how you do a table. That's how you put them on the graph. Problem 2. The graph shows the projected altitude, f of x, of an airplane scheduled to depart an airport at noon. If the plane leaves 2 hours late, what function represents this transformation? See page 100 for the graph. So on this one, you'll see that the graph is a funky graph. We don't know what that one is. All we know is that the initial one departs at noon, so that's the one in black. So initial is the black one, and the actual time is the blue one. The 2-hour delay means instead of leaving at noon, it would leave 2 hours later, which would make it at 2 p.m. This shifts the graph right to, because 2 p.m. is time, it doesn't affect the altitude or anything. So 2 p.m., this one right here, affects the time, which means right to. So we have to think back at the beginning. If you have a plus 2 behind the function, it takes it up or down, and which a plus 2 would be up. If you actually do, and that affects the y-axis, if it affects the x-axis, it affects the actual function. So if my function is f of x, and I am 2 hours late, you would have f of x minus 2, because you'd be doing 2 units to the right. So whatever the function is, that's how it affects it, is 2 to the right. How do we do reflections? A reflection flips the graph of a function across a line such as the x or y axis. Each point on the graph of the reflected function is the same distance from the line of reflection as its corresponding point on the graph of the original function. That's a lot. We'll see what it means on a graph here in just a minute. When you reflect the graph and the y-axis, the x values change signs and the y values stay the same. So let's keep track of this. Let's go a different color. Okay, so reflect on the y-axis. here's what happens to the ordered pair. The x value's sign changes, and the y values stay the same. So let's think about that in a graphing manner. So if you have a graph like this, and you have a point right here, if you reflect over the y-axis, which is here, okay, that's the y-axis reflection, your new point would be here, so it would be so many units away from there, so many units away from there. Here's your new point, your final point. So notice how if this, for instance, is 2, sorry about that, my battery's getting low, I have to plug it in. If you reflect it over the y, it becomes a -2, but the y values stay the same, so it does make sense. When you reflect the graph on the x-axis, the x value stays the same and the y changes. So reflecting on the x-axis looks like this. So here's what you're reflecting over. If you have a point right here and you reflect it over the x-axis, it moves down here. So notice the distance from the x-axis is what's different. The x value would stay the same and the y values would change because it's the vertical change. So we've got some graph examples on page 101. Make sure you take a look at those and look at the actual ordered pairs. So the first ordered pair from the black one to the green one would be 1, 1. When you reflect it over the y-axis, it becomes -1, 1. When you reflect that same black graph over the x-axis, it becomes 1, -1. So notice what part of the ordered pair changes. So problem number 3, let g of x be the reflection of f of x, equals 3x plus 3 in the y-axis. Okay, so when we look at this one, first we're going to graph f of x equals 3x plus 3. So remember, f of x is the same as y. So it's like y equals 3x plus 3. So for that one, you could do a big old table, but we know how to graph these. It crosses at 3. Remember, it crosses the y-axis at 3. The slope would be 3 over 1. So from 3, we go up 3, right 1. And I'm going to go down 3, left 1, and then we'll draw it in. Make sure you do 3 points if you're not using a ruler. If you are using a ruler, you can get by with 2. So what is a function rule for g of x? So reflection over the y-axis. Reflect over y-axis. Okay, reflecting over the y-axis is the blue one. It makes the ordered pair -xy. Okay, so whatever your ordered pairs are, we're going to flip the sign of the x, keep the y the same. So let's look at a few ordered pairs. My ordered pairs are -1, 0, 0, 3, and 1, 1, 2, 3, 4, 5, 6, 1, 6. So it tells me that I changed the sign of the x, keep the y the same. This new one becomes 1, 0. You can't change the sign of 0, so that one stays the same. You are going to change the sign of the 1, keep the y value the same. So our new ordered pairs are these, and we will graph those in purple. So 1, 0 is here, 0, 3, and -1, 6. Okay, Now that's using the actual reflection rule right there. Another thing that you can do is think about where the y-axis is. It's not giving me my colors. Okay, the y-axis is this one. So if you reflect across there, every point needs to be the same distance from it, only on the opposite side. So initially this one is 1 unit to the left. The graph would be 1 unit to the right. This one is on the y-axis, so you don't move it. But this one was 1 unit to the right, so the graph would be 1 unit to the left. So those points do react the same way, that way graphically. A vertical stretch multiplies all the y values by the same factor greater than 1. A vertical compression reduces all y values by the same factor between 0 and 1. So if it is a fractional value, it is a compression. It sinks it in. If it is a bigger value, like a value bigger than 1, and we're talking about this number right here, it is a vertical stretch. So keep track of that one. So vertical stretch multiplies y values by whatever factor bigger than 1. Vertical compression reduces the y values by the same factor between 0 and 1. So with this one, it's going to be a fractional number. With the other one, it's going to be a number bigger than 1. Could be fractional still, but it's going to be a fractional value between 0 and 1. So don't just say just a fraction, because that might be something that's bigger than 1. It could be like 1.5. That would still be a fraction. All right, so let's do one of those. The table below represents the function f of x. What are the corresponding values of g of x and the possible graphs for the transformation g of x equals 3 times f of x? So we are now on page 102. This one is kind of a graph that we don't really know what the values are, but we will check it out. All right, so I'm going to make my xy axis. All right. My initial one is this one. In the book, if you're looking at it, it goes by 2's. So this would be -5. And up here at 2. So it starts here. And it would be -2. And then it would be down 2, 3. And then up at 5, 1. And then down again at 2, 4. Oops, wait, 2, that's 3, sorry. This one was wrong. It's 3, 1. And then 5, -2. Okay, so the book went by 2's. I'm doing the actual values. So kind of a funky looking graph. What they want you to get used to is using the rules. Okay, so they're going to do a table. And they're going to give us the values. And then we're going to figure out what 3 times the value is. So, -5, 2. -2, 2. 0, -3. 3, 1. And 5, -2. Okay, so if we're going to make this thing and stretch it, remember, if the number is is bigger than 1, it stretches the y value. So we're going to multiply all the y values times 3. And that's what this 3 times the function means. So I'm going to change colors so you know that. Multiply y value times 3. Okay, so for this one, 2 times 3 would be 6. 2 times 2 would be 4. Negative 3 times, oops, no. I did this one wrong. Sorry about that. Okay, so 2 times 3 would be 6. 2 times 3 would be 6. Negative 3 times 3 would be negative 9. 1 times 3 would be 3. Negative 2 times 3 would be negative 6. I think it's easier just to do it. So if we graph these, 2, 6, or wait, negative 5, 6, sorry. We have to graph this one together, and so on. So negative 5, 6. Negative 2, 6. 0, negative 3. Or 0, negative 9, sorry. Ugh. Sorry about that. I erased the... I think it was there. Okay, so I think we're back to where we were. Okay, so I go down to negative 9, 0, negative 9, 3, 3, 5, negative 6. Okay, so here's this one. Okay, so when you look at it, it started as the pink one and ended as the purple one. So it made it 3 times bigger, and it made those y values 3 times bigger. Look at the concept summary on page 102. It just tells you what to look for. What's a vertical translation? It moves the graph up if k is positive, down if k is negative. Vertical stretch. If a is greater than 1, it stretches the y values out. If a is between 0 and 1, it compresses those y values in. A horizontal translation would be right or left. It's going to be right h units if the function is subtracting in the middle. It's going to be left so many units if the function is adding in the middle. And then the reflections kind of show it reflects over the x-axis if the negative is on the outside of the function. It reflects over the y-axis when it is in the function. So I would say probably put these in your notes somewhere. You would have to know these for a test. Notes, memorize for test. Bring questions.